Hey, I wanted to do a video explaining something called the coupling factor between coils. So to show that, I have a antenna that I took out of a deconstructed Verifone MX915 payment terminal. And I have a variety of tags here. So it's hooked up to my VNA, and you can see that this in the x-axis here, this is the resonant frequency. So it'll go from on this side it's 12 megahertz to 15 or 16 megahertz. And then in the y-axis, that's the amplitude of the draw that the tag is introducing to this coil. So I'll start with a full card size antenna using the NTAG I2C Plus test card. So the antenna for this one is around the perimeter of the card. So it's ID1 sized like a credit card. So let's bring it up to the coil. So I'm about 8 centimeters off the surface. Yeah, about 8 is like where the maximum introduction of draw is. And if I bring it down to the actual surface of the reader, I get a pretty significant draw because it's a full-sized card. So the reason for that good coupling that's occurring is because you saw the size of the reader antenna. It's around the whole perimeter of this area where the LCD would be. And it's very similar to the size of this card. So the only things that are going to affect your coupling factor, which is called K, is going to be the size of the antennas relative to each other. So if they're the same exact size antenna, they will couple well. If this antenna was much smaller, it would couple poorly. And then the other factor that's going to affect it is their position relative to each other. So if I put this right in the center, it's got a pretty good coupling. If I actually move it up to the edge so that the corners are aligned, you get slightly better coupling. And if I bring it off center, the coupling decreases. Okay. So that's with a full-size card. Let's try with a SIM-sized payment card. So that one, the size of this antenna is just this little area right here. So it is much smaller than the total size of the reader. So the coupling factor is poor in this case, but we still do get coupling. If I align them so that this is in the center and the distance between the coils up here and the coils of the tag are very far apart, then you can see the coupling factor goes down. But if I align the corners so that the turns are overlapping, I get a pretty good coupling. And that'll work for situations where you're doing normal payment form factor. But for some of the payment stuff that I'm trying to do, I've got a COM conversion prototype. So that is when you take a credit card that has a coil on module, which is this little piece. You can't see it underneath because I have it covered in tape, but the actual contact interface of this card, I melted it down and I pulled it out, and there is a coil built into there. And this one actually, I created a little repeater board that couples with the little coil and allows you to convert it into an implant form factor. So this one is even smaller than the SIM card form factor, and it also has 2 coils, which makes it a little funny. But you can see that I'm getting a read, getting coupling there. Coupling factor is not great, but it's workable. You would definitely get a read here, especially under the high power situation of this reader running in its normal operation. It's putting out a lot more wattage than this little VNA is putting out. So this gets any coupling whatsoever. Now where we start to encounter a problem is an even smaller form factor like this Apex Flex here. So these have the applets for MasterCard and Visa preloaded on them, but currently they are not activated because MasterCard and Visa have not agreed to allow implant form factor payment chips. But they could be used in a payment terminal if that functionality got activated. So let's see how they couple with a reader like this. Now I will note these Verifone MX915 readers are really unfriendly. They're very difficult to get a read with. There are better performing readers, especially ones that don't have an LCD display, and those ones will couple with smaller implant form factors like this. But you'll notice with this MX915 antenna, we are getting a slight movement, but it's like 5% of what we were experiencing with the full-sized card. So good positioning for this would be to align it so that the top of the coil meets the top of the antenna or the reader coil, and the sides of the coil meet the sides of the reader coil. You could also do in the middle like this. And the problem here is that you will get a connection, but you won't quite get enough power to do some of the more advanced cryptography type operations that are necessary for EMV type transactions to occur. So you won't get really good coupling with this. Another even smaller form factor is this is a Next, N-E-X-T implant, and it has a low frequency and a high frequency tag in it. This can't do payments, but there are similar high frequency tags in this form factor that could hypothetically do payments if the form factor was approved. And no matter what I do with this one, I'm not going to get coupling, because not only is the coupling factor, K, very dramatically small because this coil is tiny and this coil is large, I also have different shaped coils. So this is a cylindrical coil, whereas this is a flat plane coil, and we're going to experience issues with that. So with a coil this big, you see what happens. Let me pause the video briefly and switch to a much smaller coil so you can see what happens when the coupling factor changes for all these tags. Alright, so I switched out the antenna from this larger one to a much smaller one, and I'm going to try out the tags in reverse order. So this is the Next implant, and despite the fact that the form factor is different, this one's a cylindrical coil and this one's a flat plane, the way that the flux flows will go around the flat plane coil and curl back, and that will bring it through this center of this coil, which results in okay coupling. Let's try with the Apex Flex. So this one has also pretty good coupling. You'll notice that the width of this dip is greater for the Apex Flex. The Apex Flex has a different capacitance, slightly higher, and it's also a very power-hungry chip compared to the Next. So the width of this dip, as it gets wider, something called the Q factor of a coil gets larger as it gets wider, and the Q factor gets smaller as it gets tighter together, which means that the resonant frequency that this will work at, if the Q factor is smaller, then the range of frequencies is much lower. And if it's wider, it can accommodate a much greater range of frequencies. But with a payment terminal, you want the Q factor to be relatively tight so that you get the maximum draw at the target frequency, because the payment terminals do exactly 13.56 megahertz. You don't need any of this variability. So let's try the COM conversion. So that one has an even greater draw than the Apex Flex. The resonant frequency of this one is a little bit off because it's a prototype, but I'm improving that right now. So let's try with a SIM card. So the SIM card is pretty ideally suited for this coupling. The coils in these are about the same size. and you'll see we're getting a greater magnitude draw. Now before, you saw that the coupling with this full-size ID1 card was like, I don't know, maybe 20, 30 times greater than with the smaller form factors. But when the coupling factor of the antennas changes, so too does the performance of a larger card like this. So this is a very small coil. The K coupling factor of these two coils is low. So I get even worse performance with this than I did with the SIM card. I can kind of position it. I don't know, the best read I can probably get is when the corners are aligned like this. But it's still not amazing, considering the disparity in scale. And it's all because of this size of this coil compared to this coil. I also wanted to show this odd behavior I'm experiencing with when you get two peaks, and it usually happens when you have two coils in the field. So I've extended the maximum frequency that we can read on the VNA to 24 megahertz, and you can see now there are two coils in this configuration here, and one of them, this smaller COM module, resonates at like about 18.4 megahertz, and this larger carrier board type of setup by itself resonates at like 13.4, something like that. So the strange behavior that we're experiencing is both of their peaks are present. But it's not at 18.4. The secondary peak is actually much higher at 22.68. And this lower peak, the one that was experienced by just the carrier board, is actually lower. So what actually happened is basically the one peak split into one very deep peak that is slightly lower and one very high peak that is, a percentage of this, maybe a third. What I think is happening here is there is this phenomena called overcoupling. I'm not sure why it only happens when there's two coils. I would have expected it to also happen when there's one coil very close to the antenna, but that doesn't seem to happen. It's only when there's these two. And what I think is happening is when you have more inductance in a circuit, so like you have a bigger coil, the resonant frequency goes down. The same goes for capacitance. If you add too much capacitance to a circuit, the resonant frequency goes down. But what I think is happening here is it's causing a reflection from the tag into the circuit that the reader is running. And that reflection, it's called impedance, that impedance reflection shows up in the reader coil as excess capacitance. And what that means is that when it's reflecting the capacitance back into the reader coil, that will create a raised peak. Because it's kind of like adding capacitance here is like removing inductance here. So that would raise the peak up. But we still have the part that's not reflected. Say like in this case, 60-something% of the energy is coupled. So when it's lowering this peak here, it is reflecting, or it has loose coupling. And that is causing an increase in inductance in the reader coil, which would lower the peak. So it's a very odd behavior. I still need to map it out more. I'm not sure what's going on, but it's interesting. A similar thing would happen if you took two separate coils like this. So I've got the good coupling with the payment terminal card. This would be like if you had your wallet and had a bunch of cards in it. And I bring the apex in. You can see that we've like weirdly split the peak. Bring it in slowly. We split it into a lower and a higher peak. Very weird. But yeah, no, if I figure anything else about that, I'll let you know. But But hopefully this was informative.